Okay, so our next speaker is Naoki Kobayashi, who really needs no introduction in this community, and he's going to tell us about decidable and undecidable extensions of the simply typed lambda calculus.
Okay, thanks for the introduction. So this work is concerned about the reachability problem for extensions of the simply typed lambda calculus with recursion. In the paper in the proceedings, we first give simple proofs of undecidability of the reachability problem for Boolean PCF with each of these extensions. And in the second part, we give a decidable fragment of Boolean PCF with differences by using a kind of ownership types. So first, let me explain why we are interested in the reachability problem for extensions of the simply typed lambda calculus. So it is known that for pure Boolean PCF, that is a simply typed lambda calculus with recursion and Booleans, the reachability problem is decidable. And that has been used as a foundation of free automated verification tools for function language like Mochi, which we have developed about 10 years ago. So this figure shows how Mochi works internally. So given an OCaml program as an input, we first apply predictor abstraction to get a high-order Boolean program. And then we invoke a high-order model checker to decide whether this abstract program is safe or not. And if it is safe, we can conclude that the source program is also safe. And otherwise, we get an error path of the abstract program. And if the source program has a corresponding error path, then we can conclude that the source program is buggy. And otherwise, we get a new predicate to refine the predicate abstraction further. And we repeat this cycle until we eventually can prove that the program is safe or unsafe. And obviously, this relies on the decidability of the reachability problem for these high-order Boolean programs. And this works fine for pure functional programs. But if programs have some impure features like differences and high-order exceptions, then this will break down. And that is because in that case, this Boolean program also has a corresponding impure features. And then high-order model checking problem is undecidable, unfortunately. So to convince you that this is a real issue, let me show you a snapshot of the web interface of our tool Mochi. So here is a sample OCaml program, which asserts a property about McCarthy's 91 function. And for this kind of pure functional program, Mochi works fine. And indeed, for this program, Mochi can verify it in just a few seconds. And Mochi now supports a fairly large subset of OCaml, including high-order functions, recursion, algebraic data types, and exceptions. But when it comes to programs with references, it is extremely imprecise, although syntactically it does support references. So here is a program, simple program, that just creates a reference cell X and asserts that its content is 0. So this assertion should obviously succeed. But unfortunately, Mochi cannot prove that. And that is because the underlying high-order model checker does not accept programs with references, so that Mochi first replaces every dereference of integer reference with a non-deterministic integer value. And that's why Mochi fails to prove this. So addressing this kind of issue has been a major motivation of this work. And in the rest of this work, in the rest of this talk, I'll completely skip the first part of the paper and focus on the decidable fragment of Boolean PCF with references. So we consider this call-by-value Boolean PCF with references. And I omit the type system, but we assume that programs are simply typed. Okay. So the black part is ordinary function language with recursion and Booleans. And fail is a special command that aborts the program. Okay? And red part shows ordinary ML-style reference primitives. And then for this language, I believe that it is the reachability problem is undecidable. And I believe this is a classical result, but actually I'm not completely sure whether this is an appropriate reference because they consider call by name language. But anyway, our paper gives a simple proof for the call by value case. And please note here that without references, the reachability problem is decidable. And that is an immediate corollary of the decidability of higher order model checking. And we indeed now have a reasonably good higher order model checker that decides this problem, although the worst case complexity is hyper-exponential. Okay. So based on this undecidability result, we wanted to find a decidable fragment by using a type system. So the main idea was to restrict Boolean PCF with references by using a sort of linear type system to ensure that no live alias exists for references as well as for reference capturing function closures. And based on that restriction, we can construct a type-based translation from the restricted fragment to Boolean PCF without references. And that is achieved by what we call local store passing translation. That is a variant of standard store passing style translation, but we only pass around local store that is used in each function. So let me explain a little more details about that. So the first idea is to introduce ownership control for references so that no live alias exists for a mutable reference. So here, this program first creates a reference cell X and creates an alias Y of X and use X and Y afterwards. Okay? So for this program, both X and Y are live at this point, and we forbid this kind of aliasing situation. And in contrast, this is fine because although alias Y is created here, only Y is used afterwards. So in this case, only Y is live at this point. Okay? And the latter program can be converted to a reference-free program like this. So here, we just replace a reference cell with its contents, and we just remove the reference operations and replace update operation with let binding. Okay? So actually, this kind of idea has been already used in our recent work on automated verification of first-order programs with references. And this work is a sort of extension to deal with high-order functions, possibly capturing references. Okay? So to deal with functions capturing references, we also impose a linear ownership principle for reference capturing closures. So this program first creates a reference cell X, and that is captured by function f. Okay? And alias G of f is created, and G and f are used afterwards. So at this point, both f and G are live, and we forbid this kind of situation where the multiple alias exists for reference capturing closures. Okay. And in contrast, this is okay because at this point, only G is live. Okay. And the latter program can be converted to this reference-free program. So as before, reference cell is replaced with its contents. And the function f is represented as a pair consisting of its local store x, which is captured by the function f in the source program, and a code in store passing style. But only the local store x is passed around here. And in calling function g, we first extract the local store of g, and then invoke the code part of g, like this. So this also has a flavor of closure conversion. And also, we need to ensure that so this is reference-free program, and we want to also need to ensure that this is simply typed. So to ensure that we impose additional restriction, and that is to impose a static bound on the number of captured references. And that is ensured by using a type system. So here, this program creates references x and y, and creates a function f that captures reference x. Okay? And then this f is given this kind of type. And here, 1 over the arrow expresses the fact that one reference is captured by this function f. Okay? And this next function g captures reference cell y, as well as x indirectly through this function f. Okay? So that this g is given this type. So now this 2 indicates that 2 references, x and y, are captured by g, okay? Or owned by g. And then based on that information, we can convert this to reference-free, well-typed program. Simply typed program. So here, as before, x and y are references x and y are replaced with their contents, and the function f is expressed as a pair consisting of the local store and code in the store passing style, and f is given this simple type. Okay? So this part is a type of the local store. And g is also represented as a pair consisting of the local store, which is the values of x and y, and the code in the store passing style. Okay, then again, g is also simply typed like this. Okay. So based on these ideas, we have formalized a type-based translation to remove references, and prove that the result of translation is a well-typed term of Boolean PCF, and reachability property is preserved by the translation. Okay. So as a corollary, we get that for programs well-typed in our type system, the reachability problem is decidable. Okay, so, and actually the type system as formalized in our paper is quite restrictive. So in the basic type system in the paper, if once a reference is captured by a function, that reference cannot be used outside of the function, even if the function becomes garbage. So this kind of program is disallowed. But actually, we can allow this by introducing more flexible ownership control by using Rust style and or consort style ownership types. And then we can apply the prophecy-based translation of Rust Holm, which is also our previous work. Then we get a reference-free program. Okay, so let me briefly discuss applications to automated verification. So far, I have considered programs with only Booleans, but our translation actually works in the presence of other base types, such as. So we can, given programs with references, we can first apply our transformation to get programs without references, and then use off-the-shelf verification tool for pure functional programs. Okay. So to check the effectiveness of this kind of approach, we have manually translated several tricky programs and fed that to Mochi. And then we could distinguish between this kind of these kinds of programs with a subtle difference. So here, in the first program, reference cell X is first created, and that is incremented each time F is called. And in the second program, X is created each time F is called. And we can correctly distinguish between these two programs in our approach. Okay. So now let me conclude. So I have completely skipped in this talk, but in the paper, we also give simple proofs of undesirability of various extensions of Boolean PCF. And we constructed a decidable fragment of Boolean PCF by using a kind of type system. And in future work, we plan to extend this and formalize and implement it more flexible control via lifetime and also fractional ownerships. And we are also thinking about redesigning a functional language with last-style ownership types. And then our translation would work better. And also here, we focused on references. But our idea may be applicable to also some of the other effects, such as resource usage. So we plan to investigate generalization of that. Okay. So that's all, and thank you for your attention.
Okay, so we have plenty of time for questions. So who'd like to be first? Yes.
Thank you. So in Mochi, you showed at first an example where you have a reference and you over-approximate the reference by just non-deterministic value. So now that you have this translation, do you treat programs that are well-typed exactly? And if they're not well-typed, you're still doing that non-deterministic over-approximation? Or can you maybe translate a part of a program and only the part that is not eliminatable is treated as an over-approximation?
Okay. Yeah, so basically, in general, it is hard to type all the reasonable functional programs in our type system. So what we have in mind is that for differences conforming to our linear ownership principle, then we can apply our translation to remove them. And for the other references, we just leave them there and pass them to existing tool. So for differences that do not conform to linear ownership principle, the analysis remains imprecise.
So you will distinguish precise references and imprecise. Okay, cool. Thank you.
All right. Do we have any other questions? Okay, I have a question of my own. So my understanding is that higher order model checking works better for linearly typed programs.
Yes. Yeah.
So have you thought about, like sort of Mochi for Rust? Like, would you be able to get better scaling for a language that is sort of natively substructural?
Well, so that is a different issue than differences. So actually, yeah, we could possibly optimize the current high-order model checker, but actually the current high-order model checker sort of already takes into account, can take advantage of linearity without modifications.
Okay.
So we have not tested, but yeah.
Okay, thank you. So let's all thank our speaker again, and could the next speaker come up?